Okay, last week we talked about kinetic energy. And kinetic energy is pretty easy to see because there's some kind of motion, something is moving. All right, we defined kinetic energy as energy an object possesses because it is in motion. All right, so kinetic energy is currently doing work. Work is currently being done. Because remember, work is when a force pushes an object a distance. So if it's moving a distance, there has to be kinetic energy, okay? Potential energy is a little bit tougher to recognize because there's no movement, all right? It's based on its position. So potential energy is defined as energy matter can possess as a result of its position. So where it's located in a gravitational field or a magnetic field, it possesses energy. Now, potential energy is not currently doing work, but it has the potential to do work. So the object is not currently doing work, but has the potential to do work under the right conditions because of its position. Okay, so let's look at a couple examples here of potential energy. There's four types that we're going to look at. We're going to look at gravitational, magnetic, chemical, and elastic. So these are the four that we're going to look at, okay? So let's look at each one of them individually. Gravitational energy is energy a mass possesses because of its position in a gravitational field. So here on Earth we have something called gravity. Many of you are familiar with because you have fallen and gotten bumps and boo-boos, right? So because the Earth is so big and has so much mass, it has a gravitational field. Now, we have mass too, and we have a gravitational field, but our gravitational field is really small because we don't have very much mass. So the bigger the object, the stronger the gravitational field. So the Earth is a massive object, it's very big, so it has a strong gravitational field. The Moon is a massive object, it has a strong gravitational field, but it's smaller than the Earth, so its gravitational pull is less than the Earth, okay? Then you look at like a planet like Saturn. Saturn's much bigger than the Earth, so it has a stronger gravitational pull, all right? So mass is directly related to gravity, all right? And it's also directly related to gravitational energy. So there are two things that you have to think about when you're thinking about gravitational potential energy. The first is the amount of mass something has, all right? The more massive an object, the more potential energy it could potentially have. And then the second thing is the distance apart or the height. So here on Earth, the Earth has a gravitational field. So my marker here has mass, and because of its position or its height above the ground, it currently has potential energy, specifically gravitational potential energy. And right now it's not doing any work, right? There's no motion. Remember, work is force times distance. This has to travel a distance for work to take place. So when I let go of the marker, that gravitational potential energy turns into kinetic energy because there's movement. So it falls to the Earth, all right? So there's two ways we can increase or decrease the amount of gravitational potential energy. So let's look at this one first. This one's the easiest one kind of to understand. The more I raise the marker, the more potential energy it has because it's going to travel a further distance, right? So the fall is going to be further, okay? It's going to have actually a chance to accelerate more too, all right? And this should be instinctive to you. If you were laying on the ground below the marker and I dropped it from here on your forehead, it would hit, you'd rub your forehead and say, that's smarts. Well, if I go way up here and drop it and hit it on your forehead, which one's going to hit with a greater force? The one up here. You should instinctively know that the higher we put an object, the more energy we are storing or the more energy we are putting into the marker, okay? So, increase the height, increase gravitational potential energy. Decrease the height, decrease the amount of gravitational potential energy. Now, the next thing is the amount of mass. So, the heavier an object is, the more gravitational potential energy it has at the same height. So, for example, I have a marker my marker, and I have a shot put, and this weighs 8 pounds. All right, it has a mass of about 4 kilograms, a little bit less than 4 kilograms, okay? So if we hold these at the same height, and I let go of them, and you're laying on the ground, which one's going to hit you with a greater force? This one, right? Because it has more mass. It's taking more force right now for me to hold this up. This arm's kind of straining and this arm's doing just fine because this is much more massive. It has way more mass, okay? So I'm putting a force on this. Now remember, I'm not doing any work right now because they have to move a distance, all right? So I'm pushing with a force to keep it in place, but I'm not doing any work yet because it hasn't traveled a distance. So when I let go of these and they fall, I'm not going to do that because this would make a loud thud and maybe crack a tile. This is going to hit with more force, all right? It's going to do more work. I'll have a demonstration later in the week that I'll do a video of and post for you guys to watch, maybe to explain this a little bit better, okay? So just remember, gravitational potential energy. Two things you're thinking about, mass and height. As mass goes up, gravitational potential energy goes up. As mass goes down, gravitational potential energy goes down. Height's the same way. Height goes up, gravitational potential energy goes up. Height goes down, gravitational potential energy goes down. So I've embedded a YouTube video here in the slides presentation. You can watch it and gain a little bit more understanding. All right, elastic energy. So elastic potential energy is defined as energy stored as a result of applying a force to deform an elastic object, okay? So there are two types of elastic energy, or there are two ways that you can deform an object. You can compress it, so like a spring. So if I take a spring and I compress it, push it down, I'm holding it there with a force, and I've stored energy. I've stored potential energy in it. And when I let go of that spring, that spring's going to move. It's going to bounce. It's going to bounce back. Okay. A really good example of compressed potential energy is pole vaulting. So when a pole vaulter runs down the field or runs down the pole vault track, the mat, they're running, they have kinetic energy, right? They're moving, that's easy to see. Then when they take that pole and they plant it into the plant box, that pole is made out of fiberglass and it can really flex. And if you watch a pole vaulter that's really good, when they plant that pole bends. Well, they've compressed it. They've caused the two ends to get closer together. They've compressed it, okay? And that energy gets stored into the pole vault pole. It now has the potential to do work. And then when that pole vaulter, after they've bent the pole, they jump, and that pole flexes back or bounces back. And when it does that, it actually takes the pole vaulter and slings them over the bar. Okay, so compressing something. So when we take a force and we kind of compress it, we're storing energy, elastic energy, into the spring, into the pole vault pole, into a bow and arrow. Okay, all those are forms of compression. Stretching something is like a slingshot or like a rubber band. So many of you guys are familiar with rubber bands. So right now we would say that the rubber band is relaxed, or we would say it's static. Okay, there's no forces acting on it. But if I take it and I apply force and I stretch it, all right, right now the rubber band is stretched. We would say it's rarefacted. Okay, and there is energy stored in the rubber band. And it's going to stay there until I release one of my fingers, and that stored elastic potential energy gets released into kinetic energy. And it hits my finger and it kind of hurts a little bit, right? Hits my finger with a force, okay? So elastic energy, I think maybe one of the easiest ones to understand, because when something's getting compressed, hey, you should know that's elastic energy. When something's getting stretched, that's elastic energy, okay? All right, magnetic energy. An object that has the potential to do work because of its position in a magnetic field. So, we've all played with magnets before. I have some magnets up here. And these are pretty strong magnets. And you can see as I move the magnet under my hand, actually let me come around here. You guys can see as I move the magnet kind of, let me come around. You can see as I move the magnet under my hand, it makes the magnet move. So these are pretty strong magnets, okay? So these magnets can do work by applying a force, but they can also store energy based upon the position of the magnets in the magnetic field, or the position of things that are magnetic in the magnetic field. So magnetic energy works a lot like elastic energy. We have to pay attention to the poles. So you guys know that like a lot of magnets have a north pole and a south pole. And we know that alike poles push each other away, right? So if I put a south and a south together, they push each other away. All right? Well, think of that like a spring. So if I take two alike poles and I push them together here on the table, I push them together, you can feel the energy. You can feel the force of them pushing back, right? But they're not doing any work yet because they're not moving. But if I take my hand off of one, that magnetic field is going to cause that magnet to slide away. All right? So think of that just like a spring. When I compress alike poles, I'm storing energy in the magnetic field. Okay, when I compress like poles, I'm storing energy in the magnetic field. Opposite poles can be stretched within a magnetic field to increase potential energy. Think of opposite poles kind of like rubber bands. So north and south are attracted to each other. So like you can, when you get them close, you can feel them pulling towards each other. Like these, I can feel them pulling towards each other. Because when they get close, they are attracted to each other. Okay? Now, if I take these and stretch them apart like a rubber band, like that, and then I let go, you can see they move, work gets done. All right? So opposite poles that are attracted to each other, you stretch them apart like a rubber band, and when you let go, they go back together. All right? So again, alike poles is like a spring. You compress them, they'll push each other away. Opposite poles is like a rubber band. You pull them apart, they'll go back together. Now, all of this is determined by the fact that they're still in the magnetic field. Once we get past the magnetic field, there's no movement. But that potential energy is still there. So, like, I let go of these. They're outside each other's magnetic field. But that potential energy is still there because once they get back together in the magnetic field, we had alike poles there. They pushed each other away. So let's do that again. Right now they're outside of each other's magnetic field, but once we get back in the magnetic field, you see they come back together, okay? So they have to be positioned in the magnetic field.
Mackenzie Wall, Emily Riggio, office please.
All right, our last one, chemical energy, is stored energy in the bonds of a chemical substance. So, whenever a chemical reaction takes place, one of two things can happen. Actually, both can happen in the same reaction. Either atoms are broken apart or new bonds are created. So either atoms and their bonds are broken apart or new bonds are created. And in a chemical reaction, we might have bonds being broken and bonds being put back together at the same time, all right? Those bonds are energy. Remember we talked about how atoms are little tiny magnets and they get held together by those charges. Well, when we release those charges, when we break those bonds, we release that energy. When we form new ones, that energy gets stored, okay? So, right now, in all matter, there are bonds in matter, and there's chemical energy stored in everything, okay? Some of them are broken down rather easy. Some of them are not. In your body right now, you have fat cells, and those fat cells are stored energy. When those fat cells get released, they get broken down. When you burn fat through a chemical process, that energy gets released, okay? So, when bonds are broken, energy gets released. So that's how we know if the bonds are being broken or if they're being formed. Because broken bonds release energy. So when you release energy, when you release potential energy, it has to convert into kinetic energy. Because remember, energy cannot be created or destroyed, it can only change form. So when we break those bonds, the stored potential energy is going to turn into kinetic. And when that happens, we're going to see some form of kinetic energy. So we're going to have heat, light, or sound. So when bonds are broken, you're either going to see heat, light, or sound. So let's think of a couple of examples here. I told you just a minute ago, your body stores energy in fat cells. Well, when you go outside and exercise to burn fat, that's a chemical process. And when you exercise, what happens to your body? It heats up. So exercise causes a chemical reaction in your body that breaks down fat cells, that releases energy in the form of heat. Okay? Glow sticks. Glow sticks have two chemicals inside of them. One's kind of in a little vial on the inside, and one of them's on the outside in the plastic. And when you break that little vial on the inside, when you bend them and you hear that little vial break, those two chemicals mix. And it's releasing energy in the form of light. Sound. Explosions make a big boom because they release energy. They release it really rapidly. Sometimes you'll hear things fizz. Sometimes when you put acid on certain minerals, they break it down and release carbon dioxide, and it fizzes, and you can hear it fizz. Okay, so just remember, when bonds are broken, you're either going to feel heat, see light, or hear sound. Okay. On the other hand, when bonds are formed, energy is stored and the substance feels cold. So, to form these bonds, matter will pull heat energy out from its surrounding environment. And when heat energy gets pulled in, it gets stored in these bonds. So, when the substance feels cold, we know that that is forming new bonds. All right? We call this up here exothermic reaction. We call it exothermic because the energy is leaving. It's leaving the system. So it's exothermic. It's leaving in the form of heat, light, or sound. We call these endothermic because the heat is getting pulled in. In. Okay? So I've got two videos here of examples of an exothermic reaction and an endothermic reaction. Okay? All right, mechanical energy. Mechanical energy. Now, this isn't mechanical movement. Sometimes you'll see books refer to mechanical movement. Mechanical movement is kinetic energy. It's the movement of mechanical pieces. All right, when you run, that's mechanical movement. All right, mechanical energy is actually a formula. Mechanical energy is the total amount of energy in a system. Mechanical energy equals potential energy plus kinetic energy. So humans like us, we're a great example of mechanical energy because we have energy stored in us in our fat cells and in our muscle cells as well. All right? But we're also moving all the time. Our heart's pumping, the blood's going through our veins. we're digesting. There's all kinds of movement going on in our body. So to know the total amount of energy in our system, we would have to add these two together, and we call that mechanical energy. Okay? So I'm going to post probably tomorrow a worksheet on practicing identifying potential energy. So working on with gravitational energy, height and mass, with elastic energy, compressing and stretching, magnetic energy, kind of the same thing, compressing alike poles, stretching apart opposite poles. With chemical energy, identifying endothermic and exothermic, okay? You'll be able to do it as many times as you want. It'll be up for a couple days, so make sure you check the stream for that. Remember tonight, your vocabulary, energy vocabulary is due, that worksheet. Make sure you know all of those terms. There's 18 of them. You're going to have a vocabulary quiz next week. So you need to study those words, know those, and be ready for your vocabulary quiz next week. All right?